So what we've covered up to this point, we've covered parts that involve us looking at solving polynomials and how we solve those equations. What we're going to look at in this one is take a different turn. So what we're going to look at is, if I give you a sketch of a polynomial, can you tell me the equation? So judging the equation of the polynomial simply by the graph and by the sketch of it in front of you. Now it is possible, and it only requires two key bits of information from that sketch. What it needs is two features. First feature is all of the roots. Now I say all of the roots because depending on the highest power of the polynomial, you'll get more roots. So a cubic has 3 roots. A quartic, so the power of 4, has 4 roots. The highest power determines how many roots there are, and we need them all if we're going to be able to calculate the equation accurately. The second thing we need is the y-intercept. So where does it cut the y-axis? We need that in order to be able to get a second part of the equation. Now, when we're looking for the equation of a polynomial, it's always going to take this sort of form here. So y equals k bracket x minus a, x minus b, x minus c, x minus d, and so on. Now, these all come from different bits of information we get. So the brackets with the x minus a, b, c, etc., these come from the roots. So that's why we need the roots. They tell us this main part of the equation, this main thing that we're looking at. The y-intercept tells us this. So the y-intercept tells us the value of k, so this coefficient at the front of the equation. It tells us that bit of information. Now, easiest way to show something like this to you and how these bits of information come together is with a couple of examples. So here you go. First one, I want to calculate the equation of the polynomial shown in this diagram here. So the first key bit of information we look at are the roots. Now, looking at this diagram, there's 3 roots clearly. So what we can then say is that x equals negative 3, x equals 1, and x equals 4 are your 3 roots for this equation. So what we're then able to say is, if we remember the general way we write it is y equals k bracket x minus a, x minus b, x minus c, and we know it's only going to be 3 brackets because there's 3 roots, we're able to put these values in for the a, b, and c to get the first part of our equation. So what we're then able to say is y equals k bracket x minus a, so we'll make a this one, so minus minus 3, so x plus 3, x minus b, we'll make b this one, so it's x minus 1, we'll make c the 4, x minus 4. So that's the first part. We've got the brackets done, but we still have this k value. Now, the k value comes from the second piece of information that we're going to take, our y-intercept. Now that's given here. So we can read off the coordinate of our y-intercept. That's simply 0, 6. Now, how do we use this to get k? Well, what we do is we substitute the values for x and y from this coordinate in, and that gives us an equation in k that we can solve for it. So we know y is 6 and x is 0. So I could say find 6 equals k times, and put x is 0 in here. 0 plus 3, 0 minus 1, and 0 minus 4. Then we could just solve this. It's one variable. It's not even got a squared power. It's just a single variable. This is straightforward for us to solve. So 0 plus 3, so I've got 3, negative 1, negative 4. So 3 times negative 1 times negative 4 gives me 12. So I know 6 is equal to 12k. K is a half. Now from that, I can write out my full form of my equation. I know y equals a half, bracket x plus 3, x minus 1, x minus 4. So there you go. I've got my equation of my polynomial. Now sometimes it wants you to write it so there's no brackets, so multiply it out in the expanded form. Well, all you would do is multiply out the brackets, so do this pair, then this pair, and then times the whole spiel by a half. When you do that, you get 1 half x cubed, take away x squared, take away 11 over 2x, plus 6. That's what you get when you expand the bracket. Now if it doesn't ask for this, you'd be fine leaving it in this format here. Just look for that phrase, so expanded version, without brackets, something like that. Now sometimes some of the roots can add a little bit more complexity to the graph and the equation. It still isn't beyond us, but we just have to watch out for it. So I'm going to show you that now. So what I want to do is calculate the equation of the polynomial shown in this diagram, which also has the point 3, negative 72 on it. Now, if you look at this diagram, you'll see that we've got the roots as we'd expected. So we've got a root here at negative 1 and a root at 2, but we've also got this point here. Now, this touches the x-axis, and as a root we'd expect it to go through, but what it does is it turns back on itself. This is still a root, but it turns into what we know is a repeated root. Now, if you think of a repeated root, think back to something like x minus 5 all squared equals 0. Well, that would give you x equals 5 as an answer for both roots. So you would only get a single root in that equation. That's what this sort of thing means, and that's where it comes from. So we have to bear that in mind when we're working with it. Our general steps don't change. So the first one, we still look at the roots of the equation, and we still see what they can tell us. So we know one root is x equals negative 1. We know the other root is x equals 2. And we know our third root is x equals 0. But we know that's a repeated root, just by the diagram, like I say, because it turns back on itself as it touches the x-axis. So we know our general form was y equals k bracket x minus a, so one root, x minus b, so another root, and x minus c. Now, the thing is, one of these is repeated. So what we're then able to say is one of these brackets, let's say the x minus c, is squared, because it takes into account the repeated root. What we're able to then do at this point is substitute in. Now, the only thing you have to be careful of is if you've got a squared bracket like this, you put the correct value in. So it'd be k bracket x minus a, so let's make the first one a. So a is negative 1, so it'd be x plus 1. Remember, minus minus gives you a plus. X minus b would be x minus 2, and the x minus c would be x minus 0, but again, remember, it's squared with that 0. We can simplify this last bracket, get rid of the 0, and we get kx squared, x plus 1, x minus 2. That's our equation for y, so that's y equals that. Now we've used the roots to get this. We then need our second bit of information, our y-intercept, but the problem here is our y-intercept is 0, 0. If we substitute that in here, we're going to get nothing on this side, because it's going to be 0 squared times everything, which is 0. However, we are given a point of information. We are given the point 3, negative 72. So what we can do is use that in our equation, and that will help give us k. So we know we've got the point 3, negative 72. X is 3, y is negative 72. Substitute it in. So I'm then able to say is negative 72 equals k times 3 squared times 3 plus 1 times 3 minus 2. So negative 72 equals, well, 3 squared is 9, 3 plus 1 is 4, 3 minus 2 is 1, so it's 9 times 4 times 1, which is 36k. So I know 36k is negative 72. From that, I know k is equal to negative 2. So again, I can now put all the bits of information together. I know y equals negative 2x squared bracket x plus 1, x minus 2. And that's me got the format for my equation. Now again, I could multiply it out if it asked for it. So if it said without the brackets, an expanded form, that sort of stuff. If I was to do that, I get y equals 4x squared plus 2x cubed, take away 2x to the power of 4. I've written it like this because I'd have a negative at the start, and I don't like that. So there you go. That's how we get that one. So these are the key things we have to remember. First, use the roots to get this part here, and then use the point here. 9 times out of 10 it will be the y-intercept. However, slightly more complex one like this, it will give you a point of information or a key point on the graph, and we use that. So we have to make use of it all.